All right, chemistry. This is your video lecture for Chapter 8, Section 2, talking about the different types of chemical reactions. Things we're trying to get across with this section. I want you to identify combustion reactions and write chemical equations and predict the products. Identify synthesis reactions and write chemical equations and predict the products. Identify decomposition reactions and write chemical equations and predict the products. Identify displacement reactions and use the activity series to write chemical equations to predict the products. And identify double displacement reactions and write chemical equations and predict the products. So let's start with combustion reactions. A combustion reaction is a reaction of an often carbon-based compound with oxygen. For example, if we combust propane, which is a carbon-based compound, it is a hydrocarbon, C3H8, we react it with oxygen. Remember, oxygen is a diatomic molecule, Brinkelhoff, so that's going to be O2. It's going to react to yield carbon dioxide and water. And this is what we see in general when oxygen reacts with any sort of hydrocarbon, something containing both carbon and hydrogen. We see carbon dioxide and water in the products. Now, that is not necessary for it to be considered a combustion reaction. You can have a pure carbon substance, or you can have a pure hydrogen substance be combusted, as well as other things. In those situations, you're not going to get both carbon dioxide and water. You only get one. Synthesis reactions. In a synthesis reaction, a single compound forms from two or more reactants. So we have two less complex species combining to become a more complex species. We often represent this as two very, very simple or elemental species combining to become a binary compound. However, it can be more complex than that. For example, we can have two binary species combine, still becoming a more complex species, but again forming from binary compounds. Here we have ternary compound formed from two binary compounds. Another example there. We're going to decomposition reactions. In a decomposition reaction, a single, more complex compound breaks down, often with the input of energy, and we'll talk about this a little more later, into two or more elements or simpler compounds. For example, the decomposition of water. If we decompose water with the use of electricity, which is known as electrolysis, okay, electro referring to the electricity, lysis refer to the splitting, so electrolysis, we can split those two elements apart, the hydrogen and the oxygen. This is a decomposition reaction. We can have a metal carbide, not a metal carbide. We can have a metal carbonate decomposed to form a metal oxide and a carbon dioxide. This time not using electrolysis and electricity, but just using heat, which often accompanies decomposition reactions. But notice you have a more complex species being broken into two simpler species. All right, let's see how we're doing here. Predict the products and write the balanced equation and reaction for potassium with chlorine. So the reaction is most likely a synthesis reaction because, again, there's potassium and chlorine. Those are about as basic as you can get. Two elements reacting together. So if there actually is going to be some sort of reaction, they're probably going to result in a binary product. Now remember, back to our talk about ions a few chapters ago, potassium being on the left side of the periodic table is actually going to lose one electron to become a +1 ion. Chlorine, being in group 17, is going to gain one electron to become a -1 ion. And we're going to create a situation where we have K plus Cl2, again, Brinkelhoff, that's a diatomic molecule, reacts to yield KCl. All right, so you need one potassium to balance out the charge of one chlorine. So this is just a skeleton equation. Let's balance it. We'll end up with 2K plus Cl2 reacts to form 2KCl. Displacement reactions. In a displacement reaction, a single element, okay, you want to look for a single element, reacts with a compound and displaces another element from that compound. For example, we have aluminum reacting with copper chloride In here, that's the single lone element is aluminum. It is going to react with the compound, the copper chloride, and is going to boot the like charged species out. So here, aluminum, the lone element, will form a positive ion. So it's going to boot whatever is acting as the positive ion in that compound. So it is actually going to boot out copper. It's not going to boot out chlorine, because in that situation, if it did boot out chlorine, you'd have copper and aluminum bonded together. That is not an ionic compound there. It's not what we're dealing with. So the aluminum displaces copper. So for a single displacement, what is going to happen, this is an example, you're going to have a copper solution, and you can drop solid aluminum into it. And what will happen is the aluminum will actually react with that copper solution, and it will remove the copper from the chloride ions, and then it will actually precipitate out excuse me, the copper that was displaced will precipitate out, and you'll see at the bottom of this beaker right here, you see this kind of brownish metal forming at the bottom. That is the displaced copper collecting at the bottom of the beaker. Now the activity series, which is something that we're going to talk about more next section, it's simply a list that ranks the reactivity of different elements, and it looks somewhat like this. It might come in different forms, but it's going to have the same general idea. You're going to have a list of elements, and there's going to be a statement of what it reacts with. And in general, you're going to see as you go down the list, elements are going to become less and less active. And what it takes to react with, for example, if you read under reactivity there in the first row, reacts with cold water and acids to replace hydrogen, reacts with oxygen to form oxides. And you'll notice as you go down and down and down and read what it takes to react, you'll notice that it takes only higher and higher kinetic energy species, something that's very, very easily reactive. But notice at the top, those things will even react with cold water, very low kinetic energy, low on the energy scale there. And as you go down, these species will no longer react with those low energy situations. They'll take a high energy, something that's very reactive. Hot water, maybe steam even, higher kinetic energy. Or an oxide, which is highly reactive. Or an acid, which reacts very readily. But it's essentially a ranking of the reactivity of the elements included. And it exists for the entire periodic table, not just the metals, which is what we see most commonly, just to try to get the idea across. But even though here we only have metals listed, there is an activity series that extends all the way to the halogens. So let's try another practice. Magnesium is added to a solution of lead to nitrate. Will a reaction happen? If so, write an equation and balance it. So first off, let's identify the reactants. Magnesium is the species that's going to attempt to displace the lead in lead to nitrate. Now let's look at the activity series. Okay, you can flip back to the last slide if you wish to use the one here. Magnesium is more active than lead and displaces it. Okay, so for the situation we have, magnesium is listed first on the activity series, which means it's more active and will therefore displace anything below it. And we find lead below magnesium. So let's write the equation. Okay, magnesium plus lead to nitrate reacts to form lead plus magnesium nitrate. Double displacement reaction. In a double displacement reaction, two compounds in aqueous solution appear to exchange ions and form two new compounds. One of the products will be a solid precipitate, a gas, or a molecular compound such as water. Here's an example of a double displacement. Also, notice that all the compounds involved are binary, at least binary, because in order for there to be double displacement, there has to be two separate displacements. And unless there are two species that can be doing the replacing on both sides of the reaction arrow, it won't be a double displacement. Alright, and here's another chart to illustrate the double displacement reaction. Again, we have some potassium chromate reacting with lead nitrate, lead 2 nitrate. And what we're going to see is that the lead and the potassium are actually going to switch places. They're going to switch partners. Here, in the initial setup, the lead is with the nitrate, as you can see up here. But after the reaction, lead is going to be with the chromate. And the potassium, originally with the chromate, after the reaction, is going to be with the nitrate. There are two separate replacements going on in the double displacement reaction. I hope that helped. Bring any questions you have to class, and I will see you next period.